it's lovely to meet you. Who are you?
Okay, my name is Professor Winfried Hensinger. I'm head of Sussex Ion Quantum Technology Group, and I'm the director of the Sussex Center for Quantum Technologies. Now, what I do for a living is I try to build a very, very powerful machine. It's called a quantum computer. And we're in the process of actually constructing such a big machine.
You made this all public at the beginning of this year. You've created a blueprint for a super quantum computer. You created a media storm because you've come up with a whole new solution. It's modular, but it's modular with a few very important variations on other modular blueprints. Could you talk about that, please?
Okay, so maybe I should start a little bit first of how hard it is actually to build a quantum computer. The reason why it's so hard to build a quantum computer because atoms are, which we use to encode quantum information, they have to be held inside a tremendously good vacuum, in better vacuum than that of outer space. And we then hold these atoms using electric fields on top of a microchip. And this microchip allows us then to not just hold the atoms there, but they levitate above the surface of the chip, and we can move them around. And by moving them around across this microchip, we are able to build a large-scale quantum computer. Now, people around the world have tried for many, many years building quantum computers, and one of the ideas was to come up with a modular approach. You need a modular approach because if you wanted to have a quantum computer which can tackle really difficult problems, you need a lot of quantum bits. And these quantum bits, only so many can fit on a single module, so you have to have multiple modules in order for that to work. Now, traditionally people wanted to make these modules by transferring the quantum state. So the quantum state is the information on every atom. You have to transfer the quantum state from an ion, which is what holds the quantum state on the chip, onto a photon. You have to send it via an optical fiber to the next module. Unfortunately, the world record of achieving that is only 7 per second. So that's a very, very slow process to change the quantum state from one atom to a photon and send it over to another module. And what we have developed is a new approach to make quantum computers modular, where you, instead of using these optical fibers, use electric fields to transport ions, charged atoms, which hold the quantum information from one module to another. And doing so, you can achieve a connection speed which is 100,000 times faster than what can be achieved so far using these photons or light to connect these modules.
What is the scientific community's reaction been to this? I mean, there are a number of organizations out there, a number of very high-level scientists. As I said, we've come up with blueprints for a super quantum computer. What's the reaction been from the scientific community?
Actually, our work was the very first blueprint in the world to construct a large-scale quantum computer, and this is why there has been so much excitement, not just with people who hear about this, but particularly with scientists. Scientists spend a lot of years, the last few years, or the last 10 years, doing very fundamental physics in order to make quantum computers work. And this has been the first time that actually somebody has been bold or crazy or both enough to ask the question, is it possible now with current technology to build a large-scale quantum computer? So that's what we have done, and it was very, very good to get very warm reception for this achievement. But one of the things we have done in order to make sure we don't deliver just crazy ideas, we've actually deposited this idea for 3 years on what we call a preprint server. That's an instrument where other scientists can just look at these ideas and very critically evaluate these ideas. And so we asked other scientists for a long time to really find holes in this idea and to really drill holes in it. We actually very purposely asked, please be critical, please find a mistake here, find an error, what can we do? And so over some time we got a lot of ideas from other scientists and say, okay, now you need to look for that. Have you checked this? Have you looked for power dissipation in the machine? Have you done that? And so we added all of this. And then in order to have it published, it's being sent for review, so the other scientists have to evaluate that. And so they've given us more feedback, and with all of this feedback together, we've been able to come up with this plan. And this is not just a plan which we at the University of Sussex have achieved, but this has been an international collaboration where with scientists from Google, from Aarhus University, from Riken, from Siegen University. And so this team together has been able to come up with this, I would call it really a master plan, or this really bold, grand plan how to build this unbelievable machine.
So you would absolutely dispute that anybody else has come anywhere near this stage in the process?
I don't know what you mean by that question.
Yes,
so building quantum computers are very difficult, and so, but they're also something which is tremendously exciting to get together. So not a single person around the world can just go ahead and single-handedly build such a machine. So the way science works is we have groups around the world who contribute tremendous things in order to make this happen. So what we have actually done is we've taken along many of these achievements from other scientists and worked together with other scientists in order to produce something which is exciting. But this is never like an exercise where just one person goes ahead and says, okay, let's just do this. But it's really an effort where everybody works together. And obviously everybody, like in anything, has their favorite method or their technique, and so I should tell you a little bit about more quantum computing actually, because that might answer some of your questions. So over the last 20 years, people try to build quantum computers using a whole range of various technologies. And so if you look around the world, you'll find different scientists using different technologies, aiming to get to this holy grail of having a functional quantum computer. Now, in the last few years, it has crystallized that there's two technologies which have really amazing specifications. That's superconducting circuits, or superconducting qubits, and trapped ions. What I should say is that there's also other technologies, and people working unbelievably hard making these other technologies work. So in life, there's never just one way, there's many, many different ways. The building a quantum computer is unbelievably hard. So at this point in time, these two technologies, superconducting circuits and trapped ions, are really leading the field. But you never know, maybe another technology will overtake. And there's many scientists working on other technologies. So maybe we should compare superconducting qubits and trapped ions.
Yes.
Now the key thing you need to know about that is that both are actually doing amazingly well. So these are two technologies which are very likely going to produce a quantum computer. Now, but you have to make choices in life. You know, when you try to achieve something unbelievably hard, you're going to just have to make a choice. The choice I made is to investigate trapped ions. And the reason why I made this choice is because superconducting qubits, you have to cool the qubits, the actual microchip, all the way down to minus 273.15 degrees Celsius. Imagine cooling something that low. And that actually can be done. And it's a huge fridge that you make a big hole in the floor and you can make this happen. And people got amazing results with this. They made quantum computers with 10, 15 qubits. But now the question is, how are you going to go ahead if you want actually millions and billions of qubits? And what I always found very challenging to imagine having a fridge which allows us to have billions of qubits cooled all to minus 273 degrees Celsius. What I should tell you about that there are some really amazing scientists around the world who are trying exactly that, and they have my greatest support and a lot of amazement on my side at trying to do this. So this is really great work. What we aimed is to use a technology which works at room temperature, and obviously there's other big challenges in this technology. It doesn't mean like one thing is really terribly easy and one thing is terribly hard, but we recently made a few achievements. One is this modularization approach, and another innovation I'll tell you about in a second. It will take me a little bit to explain. But using these two things, we believe it got a lot easier, not easy, that's a big difference, easier to build a quantum computer. Now let me tell you about the second achievement, because that's also very important. The second achievement is about how to make computations in your quantum computer. Now let's start with a conventional computer. In a conventional computer you have a processor. Inside this processor you carry out gates. And these are logical gates done in a transistor.
Binary system.
Exactly, in a binary system. Now, there's also the equivalent in a quantum computer, these are called quantum gates. Now, in a trapped ion quantum computer, people built such quantum gates by aligning two laser beams with the accuracy of a 10th or 100th of the width of human hair on the position of these ions. And doing that, they have achieved actually the world-leading results right now. No other physical system achieved something better. But the question is, how hard will it be to build a quantum computer using this technique? And this is what many people said, hey, this is going to be so hard, that's why we're going to use superconducting qubits. Yes. And so what we've recently achieved is, and this is why we are so excited about this, we can take all these laser beams away with and instead execute quantum gates by applying voltages to a microchip. And that makes it a lot easier. Does it make it easy? Not at all. Will we have a quantum computer tomorrow? Definitely not. Will we have a large-scale quantum computer in a year's time? Definitely not. But it makes it now feasible to think about what kind of engineering would be involved in building a large-scale machine. Now that's what we have done with this first blueprint or construction plan to build a large-scale quantum computer. We actually published an approach how using these technologies you could build a large-scale quantum computer. Now this is what we're really excited about. This is what's our baby, and we are very proud that we think this is now a real engineering solution to make this happen. Coming back to your original question, you know, what do other scientists think about this? I think other scientists are first of all excited about this, the same way as I'm excited about all the other things people do in the world. Now, will they drop everything they're doing now immediately just do exactly what we do? I don't think so, because they obviously have other technologies which they also believe in, and that's a great thing, there's nothing wrong with it. What quantum computers are a means, they are a machine which can do certain things which are really going to change all of our lives. so it is, and even though I've been very excited and I'm very happy about these new technologies we've developed, it's still very hard. So it's only right that you use different means still trying to build a quantum computer, because who knows, like maybe in a year's time there is something which is going to really hold us off. So there is no, scientists tend to be very respectful about other people's work because we know how hard these things actually are. So rather than saying, okay, like, you know, only my solution is the very best and nothing everybody else is doing, it's all bad, that's a very stupid approach, because what it does is it doesn't take care of how naive humans are in technology evolution. You cannot predict what's going to happen in 5 years' time on the experimental system. So I think we've done something really big in taking out a lot of these technology challenges, and more importantly, we are now ready to start with the engineering to do that. But it doesn't mean that that we should now stop trying to investigate all the other systems, because they may well have amazing breakthroughs, you know. So, and this is how humanity advances and progresses, in order to work together. And we draw, for example, a lot of the things we do in our laboratory, we draw from other groups around the world. So, so there's amazingly smart scientists around the world who made groundbreaking achievements, and many in fact we use in this construction plan. And so this is more how you should see it. This is not really like a ego activity trying to see who's got the biggest guns or something like that, or the biggest whatever. It's really trying to make a difference for the world, and trying to achieve some kind of technology which is going to make a big difference.
What are the applications of a quantum computer going to be?
So think of a quantum computer not as a fast computer. So quantum computers are not fast computers. Quantum computers are very different machines. Quantum computers may be able to do something where a conventional computer would take billions of years to calculate. So you will use a quantum computer not to do word processing, not to send your emails, and you won't have it at home to play a few computer games. Quantum computers, there's certain quantum algorithms, quantum computing software, which allows you to do certain things which a classical computer could never do. So let me give you a few examples. So one of the things a quantum computer can do really well is factorize a number.
Yeah.
So that everybody can do that in their head, right? But if I give you a large number, it turns out even the fastest computers in the world, even a secret NSA supercomputer, could factorize that large number.
Yes.
And you know why that is really important? When you buy something on the internet, like when you put your credit card details on a website, then the encoding of your credit card details is done using a process called RSA encoding. And this RSA encoding is only safe because it's so difficult for a conventional computer to factorize a large number. Now, a quantum computer could break this encoding. Now, that's just one example, but there's many, many different algorithms. For example, there's algorithms to optimize for optimization, so optimization problems. So if you can imagine, like, there's many problems in life and you have to optimize something. For example, let me give you an example. If you're a courier company, you want to make lots of deliveries, you have to ask yourself, what is the optimal route? When can I go home quickest, right? And so a quantum computer is very good at optimization problems like this. Or in search is another example where quantum computers can search for a data set faster, much faster than a classical computer. So first of all, okay, so the most exciting thing about a quantum computer is not so actually personal, that's my personal choice, I shouldn't say this is, but my personal favorite about quantum computers is that the world around us is behaving according to quantum physics. And so that means if you want to understand something around us, like the way how molecules interact with each other, why my t-shirt has the color it has, why a material is strong or very conductive or things like that, all these things derive themselves from the quantum dynamics within the material. And so a quantum computer can understand these processes. So you can envision that a quantum computer may be used maybe to create new pharmaceuticals, to understand chemical reactions, to understand processes in biology. So this is why quantum computers are really, really exciting. And just to give you a better understanding, even more so on applications, you have to ask yourself where you are right now in the development of a technology. So if you go back to the 1940s, in the world there were around 5 computers and 50 programmers for conventional computers. How many programmers are there right now in the world? Millions. Just in London there are probably thousands, right? So right now in the world we have around 50 people writing quantum software, quantum algorithms. So you can imagine, like, the biggest quantum computer in the world right now, the universal quantum computer, has 15 qubits. So you can see where we are with this technology. And so the applications grow as the machine grows. The same with conventional computers. Nobody knew in the 1940s that we're going to have a computer in your pocket, you use it as a phone. Nobody knew there are going to be computers and ticket machines. Nobody knew we're going to have medical imaging and be able to image cancer in tissue and things like that. So these things will come out of the development of these algorithms. And so we are very naive nowadays of what are the biggest important applications for quantum computer. And they will come as we have more people developing quantum algorithms. What will this thing actually look like?
Yes. And how will people interact?
Exactly right. So let me give you some explanations on that. So right now we are in the biggest quantum computer in the world is 10-15 qubits, no more. So we are now in the process. We think we have an engineering approach to build a very large-scale quantum computer with millions of qubits, and so that's going to still take around 10 years at least, maybe 15 years to build. Many media covered this, we published this, because yes, if you want to build a large-scale quantum computer, it may be as big as a football pitch. Actually, that's the same size as one of the biggest supercomputers right now. So it's not such a crazy idea to have a big computer. We already have big computers. But obviously you're not going to have one at home because they're going to be unbelievably expensive. So what you do instead is you log on from your computer at home and you can use that machine. And you run a computation on a quantum computer which is going to be located somewhere else, as you say, in a cloud computing approach. And then you're going to run a program, and you probably pay for the time on a quantum computer, and you're not going to use it to do word processing unless you have a lot of money spare. You use it to do something what a classical computer can't do. So you're going to solve some kind of problems. If you have a company, for example, you want to offer a service none of your competitors can offer, and there's a quantum algorithm available for that, then that's why you run that on a quantum computer. And that may well give you a big advantage because, as I said at the beginning, quantum computers are not made to speed things up. They're meant to do things which you couldn't do before. And so this is in a way what you'd use them for, is you maybe be able to solve a calculation which you couldn't solve before. You'll be able to make something which you couldn't make before. You're trying to understand something you couldn't understand before. So these are very disruptive changes. And in a way, quantum computers are going to be very similar to conventional computers. Like when I grew up, and you can see the lack of hair and my age, when I learned typing, I learned it on a typewriter. And nowadays, people just smile at you when you even talk about times without a computer. Everything was different, wasn't it? You bought tickets like paper, cardboard tickets, which were printed, and no electronic ticket machines. Life is generally different. And computers, internet, email, all of that has changed things. You know, we have now electronic cameras and all these kind of things. It's a very disruptive thing what computers have done, changing our lives. And quantum computers have the potential of doing exactly that, because they're offering entirely new opportunities. They don't make things faster. You're not going to get a train ticket twice as fast. That's always going to use probably, or likely, going to be a normal computer for that. But what you'll do is you'll be able to do certain things you could never do before, and that will change our lives.
Can you talk about the very basic level, if I can use that term with quantum physics, what quantum physics is, so that anybody from the general public listening can at least get a framework in which all of this is going to operate, or is operating?
So quantum physics, in one sentence, is really weird. That's a very good definition of quantum physics. It's very strange. Einstein, very smart man, called it spooky. And for 20, 30, 40 years, physicists in fact try to disprove it, because quantum physics has some very strange predictions. Quantum physics has a prediction that an atom can be at two different places at the same time. So that atom is here and there. You can be standing here, and you can be at home having breakfast right now. So this is actually possible in quantum physics. It's not a mad quantum physics theory. I've done an experiment where I made an atom appear at two different places. One atom at two different places. Imagine you're interviewing me here right now, and you're having breakfast, but you actually generally do both of these things. That's in a way that actually exists and happens in quantum physics. And the reason why we don't see this around us, the reason why it would be fantastic, wouldn't it, if we could do all these things, is as soon as something interacts with you, we say that collapses your quantum state, and then it projects you into this classical state of you just being standing here. And but if you go on an atomic level, when you work with individual atoms, you can really shield these atoms in such a way that nothing interacts with them. And then they actually can exhibit these very strange quantum dynamics. Now, this is the essence of what a quantum computer does. In effect, a quantum computer changes these very, very strange quantum phenomena. So a quantum computer takes these phenomena and it uses them for good purpose, doing computations. The way it does it is like this. So take a classical bit, so take two classical bits, right? So you can write information into two classical bits. So imagine you have just two bits, so you can imagine you write either 0, 1 into your two bits. Okay, or you could write 0, 0 or 1, 0, but you have to make a choice. So let's assume you write 0, 1 into your two classical bits.
Yes.
If you have two quantum bits, because they can be both things at the same time, they can be 0, 0, 0, 1, 1, 0, and 1, 1, all at the same time. Now that's the really mad thing about it. It's not either or, but they're all at the same time. With two qubits, you already get 4 numbers, whereas with two classical bits, you only get 1 number. Imagine you have 10 qubits, how many different combinations you can get out of these. And that, in a way, gives rise to the amazing power of a quantum computer.
Right. So, you have started working on a prototype. What's happening next? You have mentioned in a number of your media interviews that you are trying to get the involvement of industry in terms of investment. How do you persuade industry, and what sectors of the industrial world are you targeting? Presumably to say, if you invest in this, you're going to have a benefit in area X.
So, I mean, it's not so much about the money. I think a lot of people would give a lot of money to have a quantum computer, but the key thing of building a quantum computer is not so much getting the money, but if having the right partners in order for. I'll give you an example. As you go in this exhibition, you're going to see microchips. these microchips are currently made by my PhD students, and even though they're unbelievably good, only 50% of these microchips will actually work at every single time. If you go to Intel, you'll have a facility, and at Intel, all the microchips are fantastically reproducible and they all work. And that's what we call the yield in these things. So when you build a large-scale machine, you can't just operate as a university group anymore. You have to have companies who start producing parts for you. And so in a way, what we're doing now is we're taking this from a university group kind of approach to an industrial approach. And so what we're interested in is not so much about the money, but it's about partners who have capabilities to think, as an example, to make these microchips and to work with us to make them very reproducible. But also the key thing is I would never even want the money unless I can ensure that this technology is used for the right purpose. So what I don't want is that one party just says, okay, we're going to throw all this money at you, but it's all our technology, or 50% is all our technology, and we're only going to use it to make, I don't know, like something which may not be in the interest of everybody. Quantum computers are very powerful technology, and so what I envision in a way is maybe a little model, something like, you know, Unix operating system or something like that, where people work together. And I would certainly like to assure that this technology is broadly available. And so this is in a way what makes it a little bit harder for us, because we don't want people to just give us money, but we want them to also have our same approach. And that means, for example, you don't have somebody going, you know, and saying, okay, I have the license for this medicine now, and I'm going to sell it now for £5,000 because I can, because I have the rights. So what we want to do in commercializing this technology is not just to have the resources, but primarily have the right partners to help us with the technology, but also the right partners who are keen to make this technology widely accessible.
Who would you consider the right partners to be?
I think the right partners I would think are maybe people who want to make a difference, who I don't know, have ambition to maybe do something positive for the world.
Can you mention any names?
I don't know. I couldn't really not. I mean, I have friends who I believe are following this approach, but I don't think it would be. We're really just at the starting point, and so I wouldn't necessarily want to say, hey, okay, we work with a lot of companies. We have some very, very positive relations with many of these companies, and we talk obviously about these things. But I think these are big decisions, and I mean, one of the things, for example, we're considering is having a very broad pool of supporters, so that it's not such a big financial decision. Because one of the things you have to know is, while we made building a quantum computer a lot easier, it is not something you should putting your last savings on, because it's very, very hard. It may never work. You know, it's unbelievably difficult technology to develop. And instead, I told you at the beginning of this interview, like, we hope to build it in 10 years' time. Now, if we end up taking 20 years, I'll be still a very happy man. You know what I'm saying? Like, there's a lot of, in this kind of technology development, this is not something where you can just guarantee a quick return or something like that. And you also don't want to sell snakes oil here, like, you know, in the sense of this will just do everything. And so that's the key thing. So the right investor also has to understand this is by no means, this may all blatantly fail, but it's something really exciting. And so maybe this I should list as another prerequisite. So by no means do I want somebody say, you know, okay, this is give me all your money and I'm going to give you this awesome return. That's because it may also blatantly fail, or not blatantly fail, but take a lot longer to make investment back and things like that. So God, I'm really not selling this, am I? But fundamentally, I think this is. I think maybe the perfect person would be somebody like me, generally excited about new technology. Even for Holden, I would be a bad person, because I don't think I'm financially qualifying for that kind of thing, because it's a very expensive thing. But yeah, I don't know. It's we talk with a lot of people, and there's some interest, and we don't want to rush things either. I think things like that. You don't want to just, quickly do this and start up a company and then it all falters like in 2 years because you haven't done a terrible job. So we're actually not in a rush either. So we're building this prototype in the next 2 years, and we have a whole 2 years to in fact go through this process. So I think that's a much healthier approach to do that, and also allows us to demonstrate some of the key technology parts and things like that. So
you've started building the prototype?
Yeah, absolutely.
And it will be at Sussex University?
That's right.
And how big will it be?
So it will fill pretty much a lab, like a whole room. So in this exhibition here, we actually have a very authentic model of this prototype. So this is why we came here to London, to kind of show that physics doesn't need to be necessarily boring. A lot of people, I don't know whether you have done physics in school, but a lot of physics, when I go to a party and I say I'm a physicist, and people start typically rolling their eyes, and it's usually the polite part of their physics was great, I just really hated it. So what we want to show is that physics can actually be unbelievably cool. Like, if you look into physics, like, it doesn't need to be a boring physics problem. What we do is we do calculations in parallel universes. We trap individual atoms on unbelievably complicated microchips. We do computations, and in a way, this is a little bit of what we show here is this prototype technology, but it's by no means finished. So you see, in a way, the model of a prototype here, and so at Sussex we're putting all this together now, and so we hope we'll have completed this within 2 years.
So we're talking here in Spitalfields, and could you explain about the reason for coming here? Why do you want the general public to feel closer to this technology? What's your objective in being here? So
the University of Sussex recently declared quantum technologies as one of their key priority areas, and in a way, as we are a university, and one of our responsibilities is actually to attract students not just from rich schools who are naturally gonna study a STEM subject and become immediately very rich and become the top layer of society, but we actually want to show to people, look, who maybe have not that perfect upbringing, that quantum technologies is really cool, and that you can actually go right in and you can touch things and you can hear things and you can actually excel in this. So one of the reasons why we're doing this is actually to go out. We had a few schools coming here to look at this technology, and there's nothing better like to see kids really getting excited. I got really excited about it when I was a kid. I was a nightmare for my teachers. I would keep on asking questions till they really hate me. So this is kind of what we want to do here as well, is like get people really excited about this technology and allow them to really immerse themselves completely. And also really bring it to the general public, say like people like lawyers, bankers, whatever, like, look, this is where this is. Look how amazing technology. We're not just an academic institution hidden away in the hills of Sussex, and we come out of our cave every so often with big glasses in the ugly shirt and give you a physics lecture. But I think at the end of the day, you also have to remember what we use right now, a lot of is taxpayers' money. And I think it's not justified to do this research and just to pretend I'm just very smart, I know why we're doing this. I think it's very important to actually come out and show this to people and say, look, this is what we can actually do. Look at these amazing things. And none of that would have happened if government wouldn't have invested 2 or 3 years ago quite a substantial amount of money in the UK National Quantum Technology Programme. So I want to actually say something very positive. People always criticize governments and all these kind of things, and there's ample reasons to do so. But you should also say when people get it right. And I mean, while manufacturing may be something Britain can do a little well, I don't think we are really a manufacturing nation. But one thing we are really good in is high tech. And if you look in history, like there's a lot of really high technology, amazing things which have been developed in this country. And what government has done recently is put up this program which said we don't just support the academic research, but we take this academic research and help you to put in a commercial domain. So please work with companies. So please, for example, bring this fantastic academic expertise you've gathered and make this into something which we as a country can create wealth with. And so this is another reason, for example, why we're here, because that means like you step outside our safe university environment and actually say, okay, here you go, this is quantum technologies. This is something which might be useful for you. And so this is for me a big reason, like, you know, we can't just spend taxpayers' money, we have to justify it, and I mean, this is something really, really exciting, and it's really exciting, I think, if we can just get a few more kids saying, look, physics is not just a boring thing about a mass going sliding down something and you're gonna have to do all this boring math. Now this boring math can make a quantum computer work. Like what you have a quantum computer can only work if somebody goes ahead, if some kids right now do their school math and make it happen, because as I told you, the timescale for quantum computers is 10-15 years time. So some people who go right now in high school, they're going to actually add a final count to make a quantum computer work. So in a way, you know, this is something which is also really important to you know, motivate people. We have a skill shortage in this country. Far too few people actually going in these subjects and trying to make a difference. But I'm here also to say, hey, it's not just about boring math. You can really do amazing things with this.
So you've got the support of the government in doing what you do. You work for a fantastic university who are enormously supportive. Are there any barriers to what you do? If you could change something that would open the gates a little bit more, what would it be? Or is everything in place that you need?
I mean, building a quantum computer is very hard, and there's many challenges. What would I do different? What would I like to see change? I think I'm a very content. I'm a very exciting place. It's probably the most exciting time in my life, actually, because we're really on the verge of, you know, building these machines. I struggle a bit to say, oh, but this is really horrible. I mean, there's always little things which help, but I can't think of anything which is like where I would see it's terrible. I mean, maybe, you know, this podcast can help attracting good people. I mean, we always, what we do is really hard, and so, you know, if this reaches somebody, you know, somebody who's really good with some crazy physics or some crazy math, and you say, hey, look, you know, I want to do a PhD in this field, then come, send me an email. We have lots of positions in, you know, like, get involved. Electrical engineers we need people who make things happen for us, and so this is something here. I think getting more good people, and if this also good reason as you go in the public like this is getting more people interested in this and then helping us making this happen. So this is something, but I wouldn't say I would make it different. You know, I think it's just something where I don't believe, like, in life you should complain, you should just make things better or make things different. That's what I tend to do. So
has Brexit affected you at all?
We're watching it very carefully, and I mean, one of the things with inventing really groundbreaking technology is, as I said before, is you need really bright minds. And so far I've been very lucky, so a lot of my colleagues have been complaining about the difficulty in attracting PhD students from other countries, the very best PhD students, and so far I've been very lucky with, I've got an unbelievably good bunch of students. But obviously that's very much, could be very dangerous. So it's very important that that whatever happens, that people perceive Britain as opening the doors. And what I like to say is that, you know, some of these people, in fact, in my group right now, they only make this happen. And I think Britain needs to become a high-tech nation, and we need to capitalize on this. But for that, we need really great minds, and so wherever they come from, you know, we need them, and we need to, that will really help us. Exactly, make it easy for them to come. So I think that's very important, and I mean, that there's obviously many philosophical considerations about Brexit, and obviously I feel we're always going to be better off as a big team, but and so I'm hoping personally it's going to be a very soft Brexit, with a team of Brexit, but at the end of the day we're going to just have to make the best out of whatever we're going to get. There may be also new opportunities, but I think the key message is, whatever happens, let's make sure the doors are open, because we need good people. You know, humanity is not going to advance if we don't have the very best people to make things happen.
We're standing here in Spitalfields with your quantum computer installation to reach out to the general public. along those lines, you have this great passion for physics, for quantum physics. Can you tell us what sparked that passion and a little bit about your human story? How you got to this point in your life?
Okay, so I was actually even primary school I knew I was going to study physics because I wanted to be science officer on the Enterprise, but I wasn't a trackee in that sense. I never wanted to wear a uniform or something like that. I just really generally loved developing technology, and so I think in grade 5 I already knew I'm going to study physics. In fact, I didn't even do physics A-levels because I found it a waste of time. I thought if I study physics I might as well do chemistry A-levels, so which I have to explain in Germany is possible because you get the basics of physics anyway. So but it was so I'm a very, very lucky person because I have so many friends who even now still struggle to see what they want to do with their lives. And for me it was in grade 7 I annoyed the hell out of my physics teacher because I kept on asking more and more questions till he went back in his little room and took a big book and gave it to me and said, just read this, trying to shut me up. So yeah, and my mom like always said to me, you asked a hole in my stomach. Translated from German, like, you know, I grew up in Germany. So yeah, so this very early started this fascination with physics and effect teleportation, which is now something, an ingredient we use in quantum computing. So yeah, so this is how I got myself into this, and there was never any doubting. So I lived in many countries. I grew up in Germany. I did my master's in Australia, my PhD in Australia, and part of that in America at NIST in Gaithersburg. Then I worked in America for 3 years, and then I entirely unexpected got a job offer, which I got refused from England. I had no intention ever to come to England, but it was University of Sussex, and it's a beautiful place right on the beach, fantastic climate, blue sky. And I remember actually I literally had no plan to accept this job, and I arrived and my hotel room wasn't ready, and I was sitting in the middle of December on Brighton Beach in a t-shirt, and it was the most beautiful day. And a week later I was very confused because I'd never planned to even consider England, and I fell in love with Brighton, and so then I ended up here. And I love Brighton. I love England. It's actually a lovely place, and so yeah, that's what's got me into this. And I like things which are difficult. I like to stick it to people sometimes when they say you can't do something. Then,
show them you can.
Exactly right.
So there's a competitive edge.
Oh, absolutely, absolutely. Not so much about other people, but doing things which people say you can't. Set yourself goals. Yes, yeah. and particularly when people say it can't be done. You know, you get always bit conservative people who say like, oh, that's so difficult. And quantum computing is a prime example. In fact, during my PhD, I had a colleague who looked at my experiments and said, well, this can't be done. And God, it made me work 3 times as hard. And when I worked in America, my boss looked at my experiment and again said like, oh, this is never going to work. Oh God, that got me going. And in both cases, you a favor. Oh, absolutely. In both cases, it worked eventually.
You've met an enormous amount of people during the course of your working life, doing what you're doing, particularly in the last few months with the world's media being after you. You've been on pretty much every television station and in every newspaper about your superquantum computer. Who out of everybody that you could meet in the world would you like to meet, and what question would you like to ask them?
J.K. Rowling. I think
really?
by a million years. Like, I thought you sent me an email, and I kind of never could come up with anybody, and then actually I just realized the other day it's so crystal clear. So I'm entirely, completely addicted to Harry Potter books. Like when they came out, I would read them immediately, and her imagination and her spirits is very much what moves me actually. Like so, and you can sense from her books in a way. So she's and I love, like, you know, the way the things she does and the things she says. So from not having, from all the people I haven't met, then J.K. Rowling would be probably the most interesting person to. I'd love to give a tour for my lab and then sit down for a whole afternoon and get her view of things in life. I don't have a particular question, but I'm just really impressed by it. By in a way, I think a lot of things in life are about what's the word? I don't want to use the word spirit because there's a very religious connotation. So I mean more like an attitude, a intimate goodness in people, and I think she's one of these people who's a generally good person, and so she very much impresses me unbelievably. So that would be, if I have to pick one person, then I probably want to meet her.
As a final point to all those listening who have a dream that they want to pursue, and maybe particularly those who've been knocked down and told this is impossible, what would you say to them?
When people tell you it's impossible, that's so much more fun to stick it to them. So you should just go for it. Don't ever believe anybody who tells you you can't do it. But you must have the passion. That's the key thing. You have to really love it, what you do, and don't ever give anything about what other people tell you to discourage you. Like people tend to be just afraid, of change, or they're afraid of you, or whatever. So you just follow your dreams. In fact, I can only suggest that you're gonna live for a long time nowadays, right? Who knows? Life expectancy increases. So you're wasting your time if you go for something too safe. Be a little bit daring. Be prepared to work really hard for it. Nothing ever came easy to me. I worked unbelievably hard. I can give you a whole story of my life, of all the things I was first. I was even very young. I was the very first person in Germany who got a scholarship to go to this Australian university ever, out of all the Germans from this foundation. And so I've always worked very hard and pushed the boundaries, pushed the very limits. And I think that's what you should do. Is don't go with a safe option, go with something which really inspires you. And if somebody tells you it can't be done, then just have a polite smile, don't say much, and just go right back. Just remember and stick it to them. And 5 years later, or however long it's going to take, just tell them with a little smile, and then just walk away and feel so much better. So I would say that's the key thing, is do what you dream about, and also make sure that you understand that there is no such thing as, everybody has their talents, and it doesn't make us better people, it just makes us different people, So with my talent is quantum physics, and other people's talents are playing guitar, and you really don't want to hear me playing guitar, even if I actually try. But everybody has their talent, and you should appreciate these talents and go for them. And whether you want to become a ballet dancer, or whether you want to just drive a locomotive or build a quantum computer, these are all exactly equivalent as long as you have the passion involved to achieve these. So that's my suggestion. Go with your passion, and if somebody tells you it can't be done, do it anyway. If it sounds completely impossible and you're just going to have to achieve all these mad things in order to make them happen, if you're persistent enough, you're probably going to make it happen.
Professor Winfried Hensinger, thank you very much for your time. It's been an absolute pleasure.
Thank you.
That's it.
Nice one. That was lovely.